The Nebraska plains in 1884 hit different when winter winds cut across treeless prairie. Anders Bergström learned that when his neighbor's cabin, built exactly how every homestead manual said, dropped to 35 degrees inside despite burning 8 cords of firewood, while summer turned it into a 90-degree oven. The cabin followed frontier wisdom, above-ground walls, pitched roof, standard and trusted. Across the plains, homesteaders fought the same losing battle in cabins built by the book and failing by the season. Neighbors mocked Anders's plan to bury half his walls, calling it the potato cellar house. Over 3 years, Anders quietly applied techniques from Swedish tradition and indigenous builders to create a cabin that held 65 degrees in winter using just 3 cords and stayed cool in summer with 0 fuel. I'll show you exactly how he did it. What did this immigrant understand about working with the earth that every other builder was missing? The Platte River watershed stretched endlessly in every direction, a sea of buffalo grass and blue grama that had never known an axe. When the Union Pacific brought homesteaders west in the 1870s and 80s, they found a landscape that defied every assumption about building shelter. No timber meant hauling logs from the distant Missouri river bottoms or the sparse cottonwood groves at costs that could bankrupt a claim before the first winter. The soil itself told a different story than the forested East, shallow topsoil over hardpan clay that cracked in summer drought and turned to gumbo when the rains came. Prairie fires swept across these grasslands every few seasons, leaving nothing standing higher than a man's waist. The railroad companies and territorial guides all promoted the same solution: build like you would in Ohio or Pennsylvania. Erect a standard frame cabin with lumber hauled from established mills, or construct a log cabin if you could afford to freight timber across 200 miles of prairie. The government homestead manuals showed detailed drawings of familiar structures, gable roofs, raised floors, walls standing fully above ground level, stone or brick chimneys rising high to catch the wind. Every settler who filed a claim received these pamphlets alongside their land certificates. John Harvey had followed those instructions exactly when he broke his claim 3 miles east of the emerging railroad town. He spent his first summer hauling cottonwood logs from the river bottoms, trading labor and cash for milled lumber at the depot, and raising a cabin that would have looked at home in any Wisconsin logging camp. The structure stood 2 stories tall, with a steep-pitched roof designed to shed snow, though snow rarely accumulated on these wind-scoured plains. Harvey had invested in proper foundation stones, raised his floor timbers 18 inches off the ground to prevent rot, and built his chimney from imported brick that cost him $40, nearly 2 months' wages. By December, Harvey discovered that prairie wind moved differently than forest wind. Instead of filtering through trees and losing its bite, winter gusts accelerated across the open grassland and hit his cabin walls like a continuous cold river. The raised floor that protected against rot in timber country created a wind tunnel that froze the floorboards solid. His steep roof caught every blast and transmitted the shock through the frame, rattling dishes and loosening the chinking between logs. The tall chimney that drew so well in still air created a Venturi effect in prairie wind, pulling heated air straight out of the cabin and replacing it with frigid drafts that crept through every gap in the construction. Harvey burned cottonwood, elm, and whatever scrub willow he could gather from creek beds, feeding his fireplace from dawn to midnight and still waking to ice in his water pitcher. The cabin's interior walls sweated condensation that froze into frost patterns, and his food stores spoiled from the constant freeze-thaw cycle. When spring finally arrived, the same structure that couldn't hold heat in winter trapped every degree of summer sun. The dark interior absorbed heat through the roof and walls, while the raised floor cut off access to the Earth's cooling mass just beneath the surface. Anders Bergström had watched Harvey's struggle through that first brutal winter. The Swedish immigrant carried different memories in his hands and eyes. Memories of turf houses built into hillsides in Dalarna province, where his grandfather had survived winters far colder than Nebraska's with minimal fuel. Those structures had used the earth itself as both foundation and wall, letting the ground's constant temperature moderate the extremes that surface construction could never match. In Sweden, builders excavated foundation walls below the frost line and banked earth against the exterior walls, creating thermal mass that absorbed summer heat and released it slowly through winter months. But Anders also carried the prejudices of his American neighbors. When he first surveyed his homestead claim, he had initially planned a standard above-ground cabin like Harvey's, thinking that American methods must surely improve on the old country's techniques. The availability of milled lumber at the railroad depot seemed to offer advantages that his grandfather's stone and sod construction could never match. It took Harvey's failures and a winter of watching other homesteaders struggle with fuel costs and comfort to convince Anders that prairie conditions demanded prairie solutions. The breakthrough came when Anders encountered the abandoned earth lodge sites left by Pawnee bands who had been relocated to Indian Territory. These circular depressions in the prairie showed where timber-framed structures had once stood partially underground, their walls banked with earth and their roofs covered with sod. The Pawnee had lived in these semi-subterranean homes for generations, raising families and storing food in spaces that remained naturally cool in summer and required minimal fuel for winter heating. Anders began to understand that the prairie itself offered resources that conventional homestead wisdom ignored entirely. His neighbors' ridicule began the moment he started excavating. Harvey and the other established settlers gathered to watch Anders dig what looked like an oversized root cellar, joking that the Swede was planning to live like a badger. They called his future home the potato cellar house and warned that he would wake up underwater every spring when snowmelt saturated the shallow hardpan. The county land agent questioned whether a partially underground structure would meet the homestead requirements for a proper dwelling, though the law specified only that claims must include a habitable residence, not that such residences must follow any particular architectural model. Anders pressed forward with his excavation, digging down 5 feet below grade and laying fieldstone footings that extended below the frost line. But he had not yet solved the crucial problems of drainage and moisture control that would make or break his earth-sheltered design. His knowledge of Swedish turf houses provided the basic concept, but prairie soils and weather patterns differed significantly from Scandinavian conditions. He was working partly from memory, partly from observation of indigenous techniques, and partly from educated guesswork about how to adapt old methods to new circumstances. The central question that would define his success or failure remained unanswered: how to harness the Earth's stable temperature without surrendering to the Earth's moisture, and how to create a structure that worked with prairie conditions instead of fighting them. The prairie hardpan that frustrated every other homesteader became Anders's foundation. 20 inches below the surface, the glacial clay layer formed an impermeable barrier that shed water like a slate roof, but only if approached correctly. Anders had learned from watching Harvey's cabin settle and crack that surface drainage mattered more than foundation depth. Water that pooled against foundation stones would freeze and expand, creating the very frost heave that destroyed conventional structures. The solution required thinking like water itself, understanding where it wanted to go and helping it get there. Anders began with the gravel beds he remembered from Swedish mill foundations. He hauled crushed limestone from a creek bed 12 miles north, breaking it down to pieces no larger than a man's thumb. This aggregate went down first in a layer 8 inches thick, extending 2 feet beyond the planned wall line in every direction. The gravel created a capillary break, a zone where water could drain freely instead of wicking up into the foundation stones through the natural suction of prairie clay. Above this drainage bed, Anders laid his fieldstone footings using limestone blocks quarried from the same creek bed. Each stone fitted tight against its neighbor without mortar that would crack in freeze-thaw cycles. The wall construction that rose from these footings defied every conventional technique Anders's neighbors understood. Instead of building standard timber framing and then backfilling against it, Anders constructed what amounted to a double wall system. The interior wall used traditional post and beam framing with cottonwood timbers spaced 16 inches on center, but this structural frame stood completely independent of the earth contact portion. Outside this timber framework, Anders built a secondary wall using the cut sod technique he had observed in abandoned Pawnee lodge sites. Prairie sod cut in late September held together like natural concrete. The deep-rooted buffalo grass and blue grama had spent the summer creating a fibrous mat that could be sliced into blocks 18 inches long, 12 inches wide, and 4 inches thick. Anders stacked these sod blocks in running bond pattern like oversized bricks, each course overlapping the joints of the course below. The grass roots continued growing even after cutting, knitting the blocks together into a solid mass that became stronger with time rather than weaker. Between the timber frame and the sod wall, Anders packed loose prairie soil mixed with chopped grass, creating a thermal mass 24 inches thick. The moisture control system that made this wall assembly work came from observing how prairie dog towns shed rainwater. Prairie dogs excavated their burrows with sophisticated drainage features, entrance tunnels that sloped away from living chambers, and exit holes positioned to catch prevailing winds for ventilation. Anders adapted this biological engineering by creating a perimeter drainage collar around his foundation. He excavated a trench 1 foot wide and 18 inches deep, running parallel to the foundation and positioned 3 feet away from the exterior wall face. This trench he filled with the same crushed limestone used in the foundation bed, creating a French drain that intercepted surface water before it could reach the sod walls. The splash zone protection came from Swedish farmstead techniques his grandfather had used around stone foundations. Anders built a sloping apron of packed clay and gravel that extended 4 feet from the wall base, graded to fall 6 inches over that distance. This apron, finished with a surface layer of limestone chips, directed roof runoff and wind-blown moisture away from the foundation zone. The combination of French drain and graded apron created a defensive system that kept the earth mass walls dry even during the heaviest prairie storms. Construction details that seemed minor proved crucial to the system's success. Anders oriented his cabin with the long axis running east-west, positioning the main entrance on the south face where winter sun could reach the interior and summer heat could be controlled. The timber framing used mortise and tenon joinery secured with wooden pins rather than iron nails that would rust and weaken in the moisture-laden earth environment. Every timber received a coating of pine tar rendered from scrub pine found in creek bottoms, protecting against insect damage and moisture intrusion. The earth banking technique required precise timing and technique. Anders waited until late October when the soil held optimal moisture content, damp enough to pack solidly, but not so wet that it would slump or create drainage problems. He built up the earth bank in layers, compacting each lift with a wooden tamper before adding the next. The final bank rose to within 6 inches of the roof eave on the north, east, and west walls, leaving the south face exposed for light and access. This asymmetrical earth coverage created a natural windbreak that deflected prairie gusts up and over the structure instead of driving them through wall gaps. The first test came with the blizzard of January 1885. For 6 days, temperatures dropped below zero while winds drove snow horizontally across the prairie. Harvey's cabin, despite continuous fires fed with precious cottonwood, never warmed above 35 degrees. Ice formed on the interior walls, and Harvey's family huddled in bed wearing all their clothing. 3 miles away, Anders maintained a comfortable 65 degrees with 2 small fires each day, burning less than half a cord of wood during the entire storm, while Harvey consumed nearly 2 cords in the same period. The mechanism behind this dramatic difference lay in thermal mass physics that neither builder fully understood, but that Anders had learned to use effectively. Earth temperature at 5-foot depth remained constant at approximately 55 degrees year-round, unaffected by surface weather extremes. The massive sod walls absorbed heat slowly during warm periods and released it gradually when surface temperatures dropped, creating a thermal flywheel that smoothed out daily and seasonal temperature swings. Harvey's above-ground cabin had no thermal mass beyond its timber frame, so interior temperatures closely followed outdoor conditions despite the energy poured into heating. Spring revealed another advantage of the earth mass system. While Harvey's cabin became uncomfortably warm once daytime temperatures rose above 70 degrees, Anders' structure remained naturally cool. The same thermal mass that had stored and released heat during winter now absorbed excess warmth during summer days, keeping interior temperatures stable without any active cooling. The thick walls also provided acoustic insulation that made the prairie wind inaudible from inside, creating a sense of shelter and security that Harvey's thin-walled cabin could never match. By autumn of 1885, practical results had silenced most of the ridicule from neighboring homesteaders. Anders had spent less than 3 cords of fuel during his first year of occupancy, while Harvey and other conventional builders averaged 8 to 10 cords. The labor investment in excavation and earth banking had been substantial, but it was one-time work that continued paying dividends with every season that passed. The roof system that crowned Anders's earth-sheltered cabin incorporated lessons from both Scandinavian turf house tradition and prairie fire survival. Standard homestead roofs use steep pitches designed for snow loads that rarely materialized on the wind-scoured plains, while their exposed surfaces created vast heat-collecting areas that turned cabins into ovens during summer months. Anders designed a low-pitch roof with a 6-12 slope, reducing the surface area exposed to solar gain while maintaining adequate drainage for the occasional heavy rains that swept across the prairie. The structural framework used cottonwood rafters spaced 18 inches on center, each rafter notched to sit securely on the top plate of the interior timber frame. Over these rafters, Anders laid rough-sawn planking cut from the same creek-bottom cottonwoods, creating a solid deck that could support the weight of the turf-covering system he planned to install. The planking received the same pine tar treatment as the wall timbers, sealing against moisture penetration from above. The revolutionary element came in the insulation assembly that separated interior space from exterior environment. Between the interior timber frame and the exterior sod walls, Anders had already packed loose prairie soil mixed with chopped grass, but the roof required a different approach that would provide insulation while supporting the structural loads of the turf covering. Anders solved this by creating what amounted to a suspended ceiling system using split cottonwood laths woven with prairie grass in a basket weave pattern. This false ceiling hung 18 inches below the roof deck, creating an insulation cavity that he filled with a mixture of dried grass, cattail down harvested from creekside marshes, and loose prairie soil. The turf roof installation required precise technique and timing. Anders waited for late September when prairie sod held optimal moisture and root development. He cut the sod in strips 3 feet long and 18 inches wide, maintaining a thickness of 4 inches to preserve the root mat that would hold the blocks together. The installation began at the eaves and worked upward in overlapping courses, each course offset from the one below to prevent water channels from forming. The sod blocks were laid grass side up, allowing the root systems to continue growing and knitting together into a continuous waterproof membrane. The critical innovation lay in the vapor barrier system that prevented moisture migration from the turf roof into the interior insulation cavity. Anders had observed that Swedish turf houses sometimes suffered from condensation problems when warm interior air met cold roof surfaces. He solved this by installing a layer of birch bark harvested from scattered paper birch trees found in creek bottoms, overlapping the bark sheets like shingles beneath the turf layer. This created an impermeable barrier that shed moisture while allowing the turf above to breathe and maintain its root system. Interior insulation followed techniques Anders had learned from observing how indigenous earth lodges managed the transition between earth mass walls and interior living space. Against the inside face of the timber frame, he installed a layer of split cottonwood laths arranged vertically and spaced 4 inches on center. Between these laths, he packed a mixture of cattail down, dried prairie grass, and clay soil worked to a consistency that would hold together when dry, but remain permeable to moisture vapor. This natural insulation provided thermal resistance while allowing the earth mass walls to moderate humidity levels inside the cabin. The window installation presented unique challenges in an earth-sheltered structure. Conventional homestead cabins used multiple windows for light and cross-ventilation, but Anders's design limited window openings to maintain the thermal integrity of the earth mass envelope. He installed a single window on the south face, positioned to capture low winter sun while remaining shaded by the roof overhang during high summer sun angles. The window opening was framed with doubled timbers and sealed against the earth bank with a mixture of pine tar and oakum, creating a moisture barrier that prevented water infiltration around the frame. The summer of 1885 provided the first comprehensive test of the insulation system's cooling performance. June temperatures soared above 90 degrees for 12 consecutive days, with humidity levels that made outdoor work nearly unbearable during midday hours. Harvey's conventional cabin interior reached 88 degrees by noon and remained uncomfortable until well after sunset, forcing his family to seek relief in whatever shade they could find outdoors. Anders's cabin peaked at 68 degrees during the hottest part of the day and dropped to a comfortable 62 degrees by evening without any mechanical cooling. The mechanism behind this dramatic cooling performance involved the interaction between thermal mass, insulation, and controlled solar gain. The turf roof absorbed solar radiation during the day, but transmitted very little heat to the interior because of the insulation cavity below. The earth mass walls, cooled by their contact with stable ground temperatures, acted as natural heat sinks that absorbed excess warmth from interior air. The suspended ceiling system prevented warm air from collecting in the roof cavity, while the birch bark vapor barrier kept moisture from the turf roof from entering the living space. Air quality inside the earth-sheltered cabin proved superior to conventional structures during summer heat waves. The thick walls and turf roof provided acoustic insulation that muffled the constant prairie wind, creating a sense of calm refuge that was impossible in thin-walled frame cabins. The natural materials used in construction, earth, grass, and untreated timber continued to moderate humidity levels throughout the summer, preventing the stuffiness that plagued tightly constructed conventional buildings. The economic advantages of the insulation system became apparent as the summer progressed. While neighboring homesteaders spent daylight hours seeking shade and relief from overheated cabins, Anders could work comfortably inside during the hottest parts of the day, maintaining productivity when others were forced to stop. His family consumed less water for cooling purposes and required no additional structures like shade arbors or outdoor kitchens to escape interior heat buildup. Maintenance requirements for the turf roof system proved minimal during its first year of service. The living grass covering continued growing through the summer, creating an increasingly dense mat that improved both insulation value and weather resistance. Occasional weeding removed unwanted plants that might compromise the root system. But the established prairie grasses proved remarkably self-sustaining once established on the roof surface. By autumn of 1885, the complete envelope system had demonstrated performance characteristics that contradicted every assumption about prairie construction. The combination of earth mass walls, turf roof insulation, and controlled solar gain had created interior conditions that remained comfortable year-round with minimal energy input, proving that working with natural systems rather than against them could provide superior results at lower cost than conventional construction methods. The ventilation system that controlled air movement through Anders's cabin represented an entirely different approach to managing interior climate than the simple door and window method used in conventional homesteads. Prairie buildings faced unique airflow challenges: summer heat that could kill without adequate cooling, winter winds that could strip away heating fuel faster than it could be burned, and the constant threat of prairie fires that could overwhelm any structure dependent on external air intake during critical moments. Anders designed a dual-mode ventilation system based on observations of how prairie dog burrows managed airflow. Prairie dogs created tunnel systems with multiple entrances positioned to catch or avoid prevailing winds depending on seasonal needs. Anders adapted this principle by installing low-level air inlets at the base of his south-facing wall where the earth bank met the exposed timber frame. These inlet vents, constructed with adjustable wooden dampers, drew air from the cool zone created by the earth mass walls rather than from the surface where temperatures fluctuated wildly. The outlet portion of the system used ridge vents positioned at the peak of the turf roof, designed to create natural draft through stack effect. Hot air naturally rose to the roof line where it could be expelled through adjustable openings that could be sealed completely during winter or opened wide during summer cooling periods. The critical innovation lay in the positioning of these outlets. They sat beneath the turf layer but above the birch bark vapor barrier, creating an exhaust pathway that didn't compromise the roof's weather resistance. During summer operation, the system created a continuous cooling circuit. Cool air entered through the south wall inlets, absorbed heat from the interior space, and rose to exit through the ridge vents. The earth-banked intake air remained 10 to 15 degrees cooler than surface air because it passed through the thermal mass zone before entering the living space. This natural air conditioning system moved air constantly without mechanical power, maintaining interior comfort during the brutal prairie summers that made conventional cabins uninhabitable during daylight hours. Winter operation required completely different airflow management. Anders sealed both inlet and outlet vents using fitted wooden plugs backed with cattail down insulation, converting the cabin into a sealed thermal system that conserved every degree of heat generated by the small fires he burned for cooking and occasional warming. The earth mass walls provided sufficient thermal regulation to prevent condensation problems even with minimal air exchange, while the thick insulation system prevented heat loss through the building envelope. Fire resistance became a critical design element after Anders witnessed a prairie fire sweep through a neighboring homestead in late summer of 1886. The fire had started from a lightning strike 15 miles upwind and raced across the grassland at speeds that outran horses. Harvey's cabin survived only because the wind shifted at the last moment, but several outbuildings burned to their foundations, and the intense heat cracked the stones in Harvey's chimney, requiring expensive repairs before winter. Anders had anticipated this threat by eliminating vulnerable exterior wood surfaces wherever possible. The earth banks that surrounded 3 sides of his cabin created a natural fire break that extended 4 feet from the structure in all directions. The turf roof, constantly kept moist by its living grass covering, would resist ignition even from burning debris that might land on its surface. Most importantly, Anders had positioned his chimney and flue system entirely within the protected zone of the earth bank, rather than extending it above the roofline where it could catch wind-driven embers. The flue system used a horizontal run through the north earth bank before turning vertical inside a protected stone chimney that rose only 2 feet above the turf surface. This configuration provided adequate draft for the small fires Anders burned while presenting minimal profile to catch sparks or create fire hazard during prairie fire season. The horizontal flue run also captured additional heat from the exhaust gases, transferring it to the thermal mass of the earth bank, where it contributed to interior heating. Tornado resistance emerged from the low-profile design that had developed for other reasons. The cabin's earth-banked form presented minimal wind surface to the rotating storms that periodically swept across the Nebraska plains. Where Harvey's tall cabin caught wind loads across its entire above-ground surface area, Anders' structure deflected wind up and over its rounded earth banks. The turf roof, held down by its own weight, and the root systems that anchored it to the roof deck could not be peeled away like conventional shingle or metal roofing. The tornado test came in June of 1886, when a funnel cloud touched down 3 miles west of Anders' homestead and carved a destruction path directly toward the scattered farm buildings. Harvey's cabin lost its entire roof and one gable wall, requiring complete reconstruction that consumed his cash reserves and forced him to spend the following winter in a temporary dugout. Anders' cabin sustained no structural damage despite the tornado passing within half a mile of the building. The storm revealed another advantage of the earth-sheltered design: acoustic protection that allowed occupants to remain calm during violent weather. The thick earth mass walls muffled the sound of wind and debris to levels that permitted normal conversation, while Harvey and other conventional homesteaders endured noise levels that made communication impossible and created panic among children and livestock. Seasonal solar control represented the final element in the climate management system. The roof overhang. Anders had calculated to provide summer shade while admitting winter sun worked in conjunction with the ventilation system to optimize comfort throughout the year. During winter months, when the sun tracked low across the southern sky, solar gain through the single south-facing window supplemented the small fires Anders burned for heating. The thermal mass of the earth walls absorbed this solar heat during the day and released it gradually through the cold prairie nights. Summer solar control operated automatically through the roof overhang design, which blocked high-angle summer sun while the ridge ventilation system expelled any heat that did penetrate the building envelope. The combination of controlled solar gain, thermal mass storage, and natural ventilation created interior conditions that remained comfortable without active heating or cooling systems throughout the year. By autumn of 1886, the complete climate control system had proven itself through 2 full annual cycles and several extreme weather events. Anders's fuel consumption remained at 3 cords annually, while his neighbors averaged 9 cords, and his structure had suffered no weather-related damage, while conventional buildings around him required constant maintenance and periodic major repairs. The integration of ventilation, fire resistance, and storm resistance into a single coherent system demonstrated that thoughtful design could provide superior performance across all the challenges prairie life presented. The winter of 1887 to 1888 broke every record for sustained cold that had been kept since railroad weather stations began operating on the Nebraska plains. From December 15th through February 20th, temperatures remained below zero for 67 consecutive days, with the thermometer dropping to minus 32 degrees on January 9th. Blizzards struck every week, piling snowdrifts that buried fence lines and forced livestock to shelter in whatever protection they could find. The cold penetrated so deeply that wells froze solid and had to be thawed with heated stones lowered on ropes. Harvey's cabin became uninhabitable by New Year's Day, despite burning 12 cords of precious cottonwood hauled at enormous expense from the river bottoms 40 miles away. Ice formed on the interior walls reached thickness of half an inch, and his water bucket froze solid even when positioned directly beside the fireplace. His family moved into the barn with their livestock, sharing body heat with cattle and horses in a desperate attempt to survive until the cold broke. 3 other conventional homesteads in the township suffered similar failures, forcing families to abandon their claims or accept charity from neighbors who had fared better. Anders's cabin maintained interior temperatures between 60 and 65 degrees throughout the entire cold siege while consuming less than 4 cords of fuel. The thermal mass system that had proven itself during normal winters now demonstrated its capacity to handle extreme conditions that destroyed conventional construction. The earth banks surrounding the structure created a microclimate that moderated even the most brutal surface conditions, while the turf roof continued to provide insulation despite being buried under snowdrifts that would have collapsed lighter roofing systems. The economic calculations that emerged from this winter transformed attitudes throughout the region. Harvey's fuel costs exceeded $40, nearly 6 months' cash income for a typical homesteader, while Anders spent $12 on the same heating needs. But the true cost difference lay in the infrastructure damage that extreme cold inflicted on conventional buildings. Harvey required $8 for chimney repairs where repeated freeze-thaw cycles had cracked the masonry, $15 for new window glazing that had shattered during the coldest nights, and $22 for structural repairs where frost heave had shifted his foundation stones. Anders's maintenance costs for the same period totaled less than $2, spent on pine tar to seal minor gaps where settling had occurred in the earth banks. The turf roof actually improved during the winter as the grass root systems continued to strengthen and bind the sod blocks into an increasingly durable covering. The thermal mass walls showed no signs of frost damage because their earth contact design had eliminated the freeze-thaw cycling that destroyed surface-exposed foundations. The summer that followed proved equally punishing to conventional structures. Temperatures exceeded 90 degrees for 43 days between June and August, with humidity levels that made outdoor work impossible during midday hours. Harvey's rebuilt cabin interior reached 95 degrees during the hottest afternoons, forcing his family to construct a temporary shelter in the creek bottom where they could escape the heat. Other homesteaders abandoned their claims entirely during this period, unable to endure the combination of winter heating costs and summer cooling impossibility. Anders's cabin peaked at 70 degrees during the most extreme heat, maintaining comfortable conditions that allowed normal daily activities to continue uninterrupted. The earth mass cooling system that had performed well during typical summers now proved capable of handling weather that overwhelmed every other building technology available to prairie settlers. The economic advantage extended beyond fuel savings to include maintained productivity during periods when other homesteaders lost entire work seasons to weather extremes. The vindication came quietly at first, as neighbors began visiting Anders's cabin during the worst weather periods to experience the comfort his design provided. Harvey arrived one January evening when his own cabin had become too cold for his children to sleep safely, and spent 3 hours in Anders's living room marveling at the stable temperature and absence of drafts. Word spread through the township that the Swedish immigrant's potato cellar house was not only habitable, but comfortable during weather that made conventional cabins dangerous. The county homestead inspector, Robert Mills, conducted an official evaluation of Anders's cabin in March of 1888 and documented the performance comparison in his annual report to the territorial government. Mills recorded fuel consumption figures, structural integrity assessments, and habitability ratings that demonstrated the superiority of earth-sheltered construction over conventional methods. His report recommended that homestead manuals be revised to include earth banking techniques as an approved construction method for prairie conditions. The adoption process began with immigrant families who possessed cultural memory of earth-sheltered construction from their homelands. A Swedish family named Lindström built a modified version of Anders's design on their claim 6 miles south, incorporating turf roof techniques they remembered from Dalarna province. A German family adapted the earth banking principle to their timber frame construction, creating a hybrid design that achieved significant fuel savings while requiring less excavation than Anders's full earth shelter approach. By 1890, 7 homesteads within a 20-mile radius had incorporated earth banking principles into their construction, each adaptation reflecting the builder's cultural background and available materials. The Lindströms developed an improved turf cutting technique that reduced labor requirements by 30% while maintaining insulation performance. A Norwegian family created a modular earth bank system that could be built in stages as time and labor permitted, allowing homesteaders to improve their thermal performance gradually rather than requiring the major initial investment that Anders's design demanded. The technical refinements that emerged from these adaptations improved upon Anders's original design in several important ways. The Lindström family developed a standardized earth bank form that eliminated settling problems by using a specific mixture of clay soil, chopped grass, and sand in proportions that provided optimal compaction and drainage characteristics. They established that a soil mixture of 60% clay, 30% sand, and 10% organic matter created banks that remained stable through multiple freeze-thaw cycles while providing maximum thermal mass. The legacy extended beyond individual homesteads to influence territorial building codes and homestead education programs. The Agricultural Extension Service began including earth shelter techniques in their bulletins distributed to new settlers, and several frontier newspapers published detailed articles describing the construction methods and performance advantages. Railroad companies updated their homestead promotional materials to acknowledge that prairie conditions require different building approaches than those suitable for forested regions. The principle that Anders had proven through practical demonstration that working with environmental conditions rather than against them produced superior results at lower cost became embedded in regional construction knowledge that persisted well into the 20th century. Even after conventional heating and cooling technology made extreme fuel efficiency less critical, builders continued to use earth banking and thermal mass principles for their comfort and durability advantages. The lesson that traditional knowledge, carefully adapted to local conditions, could outperform standardized solutions remained relevant long after the original homestead crisis that had prompted Anders' innovation.